I want you to shade in. I'm going to go do that with a marker. It's way too complicated. That didn't work. All right, try that again. Shade in this triangle. Oops. This triangle. And this triangle. We're going to use this diagram to model a lot of the trig identities. So if you look at your reference sheet, there are dozens of trig identities. And some of them you're just going to start to remember. And the more you can remember, the better off you are. But you can always look back at your reference sheet. Okay, I'm never going to take it away. Unless you're mean. Then I'll take it away and burn it. Okay. We want to start off by putting the reciprocal identities on the diagonals. So you have sine of theta, and the reciprocal of sine is going to be straight down the diagonal. So what is the reciprocal of sine? Cosecant. So this is cosecant of theta. What is the reciprocal of cosine? The secant of theta, 1 over the secant of theta. Oops, I'm getting ahead of myself. Sorry. Secant of theta. What about the reciprocal of tangent? Cotangent of theta. All right. Let me lock this. Okay. So now we're going to go through and write all of these identities. And notice in the center of this hexagon is a 1. So the reciprocal identities, you just follow them across. Sine of theta is 1 over the cosecant of theta. And I can also go backwards. Cosecant of theta is 1 over the sine of theta. I could go the other direction. What's another one? Tangent of theta is equal to 1 over the cotangent of theta. Go ahead and fill in all 6 of those. You can double check your answers if you look at the reference sheet. The reciprocal identities are right there. So I'm actually going to turn that into a picture. Okay, the next one, Pythagorean identities. So put your pencils down for a second. Let me show you something. Those of you who are in my class, you might remember this. Last year we talked about having a wall, and up against the wall was a ladder. And then we had this story where we pulled the ladder from the base and we created this right triangle. And we had the ground here, we had the wall there, and we had the ladder here. And we found out that it's really nice when the ladder is length 1. For instance, the sine of 30 degrees is 0.5. The sine of theta in this story is wall over ground. So this 0.5 is a percentage. It means when theta is 30 degrees, the wall is half of the ladder. So if I had a particular triangle and this was 8 with a 30-degree angle, how tall is the wall? It would be 4. If I change that 8 to a 13, how high would the wall be? 6.5. But what if the wall was length 1? How high, sorry, the ladder is 1. How high is the wall? half of 1, which is 0.5. Now, notice that this number matches that number. When the ladder is length 1, the percentage is equal to the side length, which means, oh my goodness, I am all over the place. Speak up, child. I'm sorry. Wall over ladder. Okay, are you unconfused now? Okay, I'm sorry. Dave Bird, you have my apologies. Wall over ladder. Well, if the ladder is 1, then wall over ladder is just wall, right? So when the ladder is 1, the sine of theta is the wall. So I can go back to my original problem. If I erase the ladder length and I put 1 up there, then this becomes the sine of theta, and this becomes the cosine of theta, as long as my theta is right there. Right? Well, we're going to be dealing with a lot of identities. The most important identity is probably the Pythagorean identity. So when the ladder is length 1, we have this arrangement in a right triangle, regardless of the size of theta. So this is A, this is B, and that's C. So I can take the formula A squared plus B squared equals C squared and turn it into, oh, I actually want to switch those, but not a big deal. Sine squared of theta plus cosine squared of theta equals 1 squared, which is 1. What that's suggesting is take any angle, plug it into the sine and square it. Plug it into the cosine and square it, and add them together. And you will always get 1. For instance, so the sine of 48 squared plus cosine of 48 squared. Oops, the squared has to go on the outside. Oh my goodness. I very much don't like this mode calculator. There we go. And it's 1. No matter what angle you plug in there, it's going to be true. So I could plug in 6,000 and square it. I could plug in 6,000 and square it. Oh boy, what did I do wrong? Oh, oh my goodness. Try that. Whatever. It works. I'm sure. Okay, so we can actually see this Pythagorean identity in this arrangement we've made over here. Okay, if you look at the black, the shaded in triangles, if you square the top corner, both top corners, and then add them together, they equal the bottom vertex. So you look at any black square, any shaded square, the square of the left top corner plus the square of the right top corner is equal to the bottom corner. So sine squared of theta plus cosine squared of theta equals 1. So that's the first Pythagorean identity. Okay? If we switch shaded triangles, and now we talk about this one, what would that identity look like? So the top left squared plus the top right squared equals the bottom squared. Tangent squared of theta plus 1 equals the secant squared of theta. So we're looking at this triangle here. top left squared plus top right squared equals bottom squared. This is only true of the shaded triangles. Okay, so the last one is going to be 1 plus cotangent squared equals cosecant squared. And there should be thetas in all these. Hopefully I don't forget to write them. Now, you can see those on your reference sheet. On the third column, about a third of the way down, you see the Pythagorean identities. But these Pythagorean identities can be rearranged in lots of ways. So the first one equals 1. Could the first one equal sine squared? So we could do sine squared of theta is equal to 1 minus the cosine squared. Could it be written another way? Cosine squared of theta equals 1 minus the sine squared of theta. Okay, how can the second one be written? Tangent squared of theta equals secant squared of theta minus 1. Or 1 equals secant squared of theta minus tangent squared of theta. So you can use any one of these. You can always take an identity and adapt it to the needs that you have, which is something we're going to end up doing here in just a little bit. So the last one, 1 equals cotangent squared, or sorry, cosecant squared minus cotangent squared, or cotangent squared equals cosecant squared minus 1. Okay. Everybody's following so far. This isn't difficult yet, right? Okay. The next one's also really easy. The product identities say any vertex can be created using the product of the two adjacent vertices. So any vertex can be created using the product of the one to the left and the one to the right. For example, sine can be created using tangent times cosine. Sine of theta equals tangent times the cosine of theta. What's another example? So cosine is sine of theta, cotangent of theta. The cotangent of theta is cosine of theta, cosecant of theta. Cosecant of theta is cotangent of theta times secant of theta. And we can do the last two. Secant is cosecant times tangent. And tangent would be sine of theta times the secant of theta. Again, all of these can be found on your reference sheet. So they're all on there somewhere. Now we're going to start proving identities. And hopefully I have a write-up somewhere. This is not good. Oh well. Okay. So here are all the product identities. We now need to prove each of them. I don't want you to rewrite them. So let's prove the first one. That. So down below, I just want you to write sine of theta is equal to, my recommendation for all of these, for these problems and others that we're going to be looking at, is convert to sines and cosines. Okay, if you have a tangent, if you have a cotangent, don't convert to tangent. Convert it straight to sines and cosines. So tangent, what's another way to write tangent? Sine over cosine. So what's another way to write cotangent? Cosine over sine. That would be my first recommendation. And if you try something and it doesn't appear as though it's working, stop and try something else. Because there are an infinite number of ways to prove these, and sometimes you make things really, really complicated, and you can still get the answer eventually, but it makes more sense just to stop and try something new. Other than that, you're pretty much on your own. So we'll practice a whole bunch of these. So, is there a better way to write the cosine of theta? Probably not. We could write 1 over secant, or a host of other things, but I'm not going to bother. Is there a better way to write tangent? So cosine of theta times sine over cosine, and cosines cancel, and I've just proven that sine equals sine, and I'm done. So your goal is to make the two sides equal each other. Okay, well, let's do cosine. Should I change sine? No. Should I change cotangent? Yes to what? So sine of theta, change the cotangent to cosine over sine, and the signs cancel. Would you like to see a longer way to do that I don't recommend? Just watch. Sine times 1 over tangent. Well, can I convert tangent to be sines and cosines? Yes, this is the same as sine over cosine. But now I have 1 divided by sine over cosine, so I flip it. Cosine over sine. This goes away, and now those cancel, and I have cosine. I wouldn't recommend that. If it looks like it's getting hard, stop and try something new. Cotangent. So cotangent of theta, which one should I change? So cosine of theta times one over the sine, which becomes cosine over sine, which happens to be cotangent. Cosine over sine is the cotangent. Okay? So we've done this one. Cosecant of theta. How should I change this? Good. We're just go straight to sines and cosines. Cotangent is cosine over sine. Multiply that by the reciprocal identity of secant, which is 1 over the cosine. Cosines cancel, which is 1 over sine, and 1 over sine is the cosecant. So we're done. Okay? I'm going to leave the last two for you to do. Look at your next worksheet. Oh, last one. So, any of those formulas on either of the two reference sheets are fair game. You're probably going to be using the Pythagorean identities a lot, the reciprocal identities, and the tangent and cotangent identities. And then we're going to extend it to include sum and difference identities, double and half angle identities, and others. Number 1, we want to prove that tangent of theta is the cotangent of theta plus the tangent of theta. One thing that is a good idea is to look at your answer and say, does that answer show up on one of the reference sheets? Do you have anything that equals the secant squared of theta? So I've lost my reference sheet. Oh, there it is. So if we look at the Pythagorean identities, right here is the secant squared of theta. So if I can make the left side of this look like tangent squared plus 1, then I'm done. So convert to sines and cosines. That's usually the best way. So sine over cosine times cosine over sine plus sine over cosine. Now what should I do? Hold on, we can't cancel yet. I need to distribute. So I need to distribute both of those. So the left one is sine cosine over cosine sine. What do you notice about that? It cancels to be 1. So this is 1 plus, what is sine times sine over cosine times cosine? Sine squared over cosine squared, also known as tangent squared. I'm done. I have just created one of the other identities on this on the reference sheet. Now the nice thing is, back when we did geometric proofs and most other mathematical proofs, you are only allowed to use the given and all other proven formulas and theories. But in this case, we assume all of the formulas are true. So any formula is fair game to prove another, which makes things a lot easier. Okay, everything is a given, essentially. So you're allowed to use anything you want. And again, if it gets complicated, don't do it. Stop and start over. Number 2. Is 1 minus cosine squared anywhere on the reference sheet? Well, it's not on this reference sheet, really. But if I take the first Pythagorean identity and alter it a little bit, I can make it work. If I move the cosine squared to the other side, then I have sine squared of theta equals 1 minus the cosine squared of theta. So what I'm trying to do is create a sine squared on the left side, and then I would have proven it. I'd be done. So, what should we do? Turn the tangent into sines and cosines. Sine squared over cosine squared times cosine squared. Oh, how nice. Now I'm done. Does anybody not understand how to adapt that Pythagorean identity? It's on your hexagon sheet. It's one of the 9 formulas we put on the hexagon sheet. So the red reference sheet is a simplified version of all possibles. So sometimes you have to look at the red reference sheet and adapt it to match your problem to make things a little bit easier. Okay, number 3. Let me show you what not to do. Put your pencils down. Let's say I want to turn that cosine squared into a secant. So I could do 1 over secant squared divided by 1 minus sine of theta. So that I can put this over 1, and I could invert and multiply. So cross this out and get 1 over 1 minus the sine of theta. Multiply that out, and I get 1 over secant squared times 1 minus sine of theta. So this is 1 over cosine. So 1 over cosine squared times 1 minus sine of theta. Multiply that in. 1 over cosine squared minus sine of theta over cosine of theta. And all of this is underneath a 1. Right? Well, oh, cosine squared. So the bottom is 1 over secant, secant squared minus, I have a tangent times a 1 over cosine, also known as a secant. And you can see that this is kind of a pain. I could follow that through and make it work, but I don't want to. If it starts to get too complicated, stop and try again. Okay? There's usually an easy way to do it. So let's look at the answer. Is there a 1 plus sign on the reference sheet? No. Is there a 1 minus sign on the reference sheet? No. There's a 1 minus sign squared, and those are different. So don't get your 1 minus signs and your 1 minus sign squareds mixed up, because they are different. Okay? So in this case, we're just going to have to manipulate until we end up with 1 plus sine squared. We've got to go all the way to the end. We can't skip that last step. But it's usually not too bad. What would you recommend? Don't change the cosine to a secant. It's a bad idea. Yes? So you're saying take this and multiply over here and multiply it here so those cancel? You can. It's considered bad form. Well, because if you do that, you're assuming that the denominator is not 0, right? So, well, this is not allowed to be 0, correct? That would create an undefined function. So this is essentially the same thing as cross multiplying. And in this case, cross multiplying is not considered a standard practice because that's assuming that the denominator is not 0. Anyway, to make a long story short, it makes it too easy. So when you solve these, you're only allowed to manipulate one side. It doesn't matter which side you manipulate, but you're only allowed to manipulate one side. Okay? Because a lot of the little tricks you need disappear if you end up doing the multiply trick. It does make things a lot easier, but in the math world, you're generally not allowed to do it. So, don't. Okay. Does cosine squared show up on the reference sheet? Kind of. We can adapt the first Pythagorean identity to make it work. So what is an equivalent statement to cosine squared? 1 minus the sine squared of theta over 1 minus sine of theta equals 1 plus sine of theta. Does anybody see it? I mean, you're okay with what I've done so far? So look at the first Pythagorean identity. Sine squared plus cosine squared equals 1. We want it to say cosine squared. So we moved the sine squared to the other side. And then use substitution. Okay, help me out. X squared minus 9. Does that factor? How does it factor? X plus 3 times x minus 3. Okay, what about 1 minus x squared? How does that factor? One minus x and 1 plus x. So, How does 1 minus sine squared factor? 1 plus sine squared, or sine, 1 plus sine, 1 minus sine, over 1 minus sine of theta, and I'm done. Yes, there are lots and lots of little tricks you need to remember. And this is great preparation for calculus. You might ask, these are already true. Why are we bothering to prove things that we already know are true? And the answer is, in calculus, when you're doing trigonometry, so you're performing calculus on trigonometry, it's really hard to do. So what you end up doing is altering your equation to a version that is easier to do. Sometimes you go from impossible to possible. So you need to know how to manipulate all these trig functions, or when you get to calculus, you'll be dead in the water. Because you'll look at the calculus problem, and you understand all the algebra, but unless you can change the formula to match something that's easy to work, then you're stuck and you can't go on. So we're just practicing how to use trig so that when you move on to calculus, it'll make a lot more sense. Okay, I'll do one more. Number 4. Oh, 4 is way too easy. Let's do number 5. Number 5. How? You could manipulate the right side. It doesn't really matter. So try the left side. If it doesn't work, try the right side. Which one do you guys want to do? The right side? Okay, I'll show you both. How about that? So I'm going to change these to sines and cosines. Sine over cosine plus cosine over sine. Well, I don't like that it's over 1. Under 1. Okay? So 1 over 1 times, well, that doesn't really work. You can't flip them separately. Okay, never mind. Forget that. We need to find a common denominator. So the common denominator is cosine sine. So 1 over cosine sine. So what does this side need? A sine. So it would be sine squared plus, what does the other side need? A cosine, so it's cosine squared. But wait a minute. What is sine squared plus cosine squared? Look at your formulas. 1. So 1 divided by 1 over cosine sine. Well, now I'm dividing two fractions. So now I can invert and multiply. So cosine sine over 1. So I now have cosine times sine. But I want sine over secant. So is there another way to write the cosine? 1 over secant. So it's 1 over secant times sine, which is the answer I was looking for. So let's try to do the other side. Sine of theta over 1 over cosine of theta. So I can put the sine over 1 and invert and multiply. So I have sine of theta times cosine of theta. Oh, yeah, the right side's a lot easier. That left side is kind of messy. So what you have to do, can sine be written in terms of tangent? So tangent is sine over cosine, which means that sine is cosine tangent. So that's what you would do. You would plug cosine tangent in there, And then you get cosine squared tangent, and then you work that down, but that's no fun, so don't do that. Okay, just work on the first page tonight. You can turn in that hexagon one if you want, but it does have those Pythagorean problems in there, so whatever you'd like.